in California. I've spent my entire career in Silicon Valley, and I have never worked with a single native Californian in terms of engineers. Everybody from California is from somewhere else. This is true of New York too, to a degree, but it's even more true in California. And so what that means, because any engineering team is essentially drawing people from all over the country and the world, that means that the surest way to divide an engineering team, the surest way to set brother against brother and brother against sister and sister against sister, the fastest way to do that is to bring in a pizza. Because when you bring in a pizza to an engineering team, you are actually asserting the dominance of one region over another. And someone's hometown has just been insulted, and it is the gravest possible insult, and it is Serbs against fucking Croats in a nanosecond. So we can't have nice things at our meetups. We can't have, this is a fine New York style pizza that we are not permitted to have. And I'm a non-combatant in this, by and large. But watching the Chicagoans against the New Yorkers and so on, anyway, it's ugly. It's ugly. It's great to have non-controversial pizza out here. We're going to take kind of an odyssey here. Those of you who have never seen me present before, don't necessarily know me. I have been in OS development for about 20 years. Amazingly, I actually just turned 40, which is really troubling. If you think I look 12 now, you should have seen what I looked like when I was actually 22. I mean, I actually did look like an infant, effectively. I'm 40, I've been around for a while, but I always enjoy looking at technology historically. So we're going to go on a couple of historical odysseys. And I am going to tell you the story of a technology that we have built, and I'm going to give you the honest story, the honest origin story, for a change. Whenever, and I have done this myself, I'm guilty of this myself, but when you stumble across something great, where you effectively get lucky, and you make some important discovery or develop some important technology, you always kind of retrofit your thinking to be like, oh yes, of course, this is exactly the problem I was seeking to solve. But that's rarely the case. So I'm actually going to tell you the problem you're actually seeking to solve and how we ended up with this technology. And we're going to start off with a show of hands. How many people get this reference? Your computer fell into my data. Your peanut butter fell into my chocolate. Oh my God, that is complete. So can someone raise their hands out of sympathy? Your peanut butter fell into my chocolate? You two great tastes that taste great together? It's like, okay. I'm glad that at least some of you are playing along. But so this is an ad from the 80s, and I'm really dating myself more than anything else. So it's not your fault if you don't get this. So anyway, let's just move right along. So I want to start with the prehistory of the file system, and actually we're gonna do the prehistory now, and then we'll do the prehistory actually in a little bit. But so the file system, when it was originally developed in the 70s, you had bigger and bigger disks, and there was this idea that you would just make disks bigger. I don't know if you've ever seen the IBM RAMAC. If you ever get a chance to go out to Silicon Valley, you definitely want to go to the Computer History Museum in Mountain View. There's very, very little to see in Mountain View. Mountain View basically needs a nuclear weapon, with the exception of the Computer History Museum, which is amazing, amazing artifacts. And they've got the IBM RAMAC, which is the first hard drive, 1956, and you've got these huge platters. And what they did from 1956 through the 70s and early 80s, they were just increasing the density and decreasing the size a little bit of these drives, but basically getting single drives that were denser and denser and denser. And that ran out of gas in the 80s. And in the 80s, it was clear that just as having microprocessors as well, right, where it's you just can't make a single thing that is arbitrarily big. You actually need to take some of these smaller things, and we need to start to string them together. So that's what happened in the 1980s, and that was Patterson developing RAID, a redundant array of inexpensive disks. If you buy disks, or if you're in a position where you buy disks for a living, you may well forget that the I stands for inexpensive, because your storage vendor definitely seems to have forgotten that. And actually, there are storage vendors that will tell you, no, it's independent disks, not inexpensive disks. I don't know where you got that. It's I got that from history, you asshole. Paying for another down payment on your next boat. But it was a redundant array of inexpensive disks. And the thing that's interesting to me, and this is very telling about software to me, is that the file systems in the 1980s were very young. right? The oldest file system was no older than a couple of decades, and there's no file system that was really around that long. Most of the file systems in use in the 80s were 10 years old or less. And yet, that was so old for software and so intractable that the idea of rewriting our software around this changed hardware notion was just impossible. Like, we can't rewrite the file systems. We need to do what we've done many times over in computer science, and we will continue to do many times over. Why actually rewrite it when we can just lie to it? It doesn't know. It's just software. We'll tell a very convincing lie. And that lie was volume management. Volume management was born. And what we're going to do is we're going to take a bunch of disks, and we're going to make it look like one disk. It doesn't know. So the file system is sitting on here, and it thinks it's happily talking to one disk. And meanwhile, you're talking to many disks below here. And there are good reasons for doing this. Often lies start off with good reasons. And if you can get away with it, maybe that's the end of it. But the reason we don't go around lying, aside from the fact that it's wrong, is that it also doesn't work very well. And these things tend to catch up with us. And this lie also caught up with us. This lie kind of caught up with humanity. Because what happened was you had the software that could see all of the structure of the data was just convinced it was sitting on one disk. But you're actually sitting on 10, 20, 30, 40, 50, 100 disks. Well, what happens when you want to go make this larger? Well, the software's like, disks don't get larger. That doesn't happen. It's not like it grows a platter. It's not like two platters in the spindle start feeling affectionately towards one another, spend a couple nights together, and all of a sudden you have, like, surprise, 2 new platters. But no, it's like that doesn't happen. The disks don't grow. So you couldn't actually grow a file system. Right? File systems were effectively static. You definitely couldn't shrink a file system. Parts of disks don't disappear. And you had all these other problems where this volume management layer was having to do more and more and more and more and more, and didn't have any semantic information. So things like snapshots are really hard. Things that administration is a nightmare, because you have to go administer these two things, one of which gleefully does not know about the other at all. So this became really, really, really burdensome. And by the time we got to the, I think we'll fast forward to excuse me. There we go. So by the time we got to, this is over the 1990s, and just spelling out some of the deficiencies, this was getting obviously really, really bad by the late 90s. So if you've been around as long as I have, or you remember some of these systems, and you deployed on things like VXFS on top of VXVM, or UFS on top of LVM, or IBM's LVM, you have these logical volume managers that you probably are still in therapy over at some level, because these things had really nightmarish failures where your data would be gone at the end of it, which is that's not funny. That's really, really troubling. And a major problem between this divide, this kind of semantic divide, is that when you are writing, the interface between a file system and a disk is just a block. Write this block, write this block, write this block, read this block, read this block, read this block. Well, that's a very narrow kind of semantic interface. And there's one does not have a real way of checking the other. So a file system, you can, if you want to actually protect against kind of physical errors in the volume management layer, so you want to protect against bit rot, right? Well, you can do that relatively easily because you can take a block and you can checksum it. But what if you at the volume management layer want to detect, say, a phantom write? So a phantom write is a write that actually didn't happen. You did the write, you told the controller to write, it told you I wrote it, and you said, seriously, like it's on stable storage? And the controller was like, seriously, would I lie to you? It is on stable storage. And then you go back like, okay, hey, I need block 65. They're like, I don't know what the fuck you're talking about, man. What are you, who told you that? I didn't tell you that. Like, where did you, it's like, firmware. But these are real problems. Phantom reads. You read block 63. How about block 36? The problem with that is it's totally self-consistent. So the volume management layer is like, looks good to me. I don't know. Sure. Passes up to the file system. File system's like, whoa, no, that's like Etsy password. That's not the database. And if you remember, from this era, I probably had at least one of these, but it is terrifying when you go into the database and you see Etsy password, or vice versa. It's like, no, something is very wrong in the animal brain. And the problem is those errors can be very, very deep in the stack. So the problem here, the problem with the manageability, there was the performance problems, the complexity problems. The problems were in the abstractions. This volume management abstraction, which really should have been invented as a short-term crutch, had become a long-term solution. And the tragedy is actually that still today, people are still living with this divide. And it's a tragedy because we at Sun, I was at Sun Microsystems for 14 years, saw this problem and wanted to go do something quite radical. Actually, we can go past that. And we developed this thing called ZFS. So how many people have heard of ZFS? Oh, thank God. How many of you actually deploy ZFS? Right, don't be embarrassed. It's fine. I know. That's an impressive number. But sadly, we are now in this. We are in this kind of awkward scenario where many people have heard that there is a cure for polio, but they have not actually vaccinated themselves or their children, and they keep being stricken with polio. And they know to be sad about it, and they know to be like, God, if we'd only had the vaccine. Oh well. It's like, unfortunately, like my manager won't let me have the vaccine. I hear there's like a licensing issue with the vaccine or something like that. I don't even know. So sadly, we're not vaccinated, and actually there's a very good Ars Technica article you may have seen earlier this week going into the history of ZFS and the knockoff that was created of ZFS called BitterFS, if you're bitter about it, and actually it was. The article was actually very well written and went out of its way to call them next generation systems, not new systems. The article was very upfront about pointing out that these systems have been around for a long time. My data has been exclusively on ZFS for well over a decade at this point. Exactly. ZFS was a total rethink of this divide. And as long as I had known, I came out to Sun to work with this engineer, Jeff Bonwick. As long as I had known Jeff, he wanted to completely annihilate this, and he wanted to go completely rethink this problem. And so what he and Matt Ahrens and some other engineers did is they literally went back to a clean sheet of paper, and how would we design this given that we have multiple disks are a fact of life. Also, by the way, the other kind of fact of life that's important is that we see DRAM is actually, there's a lot of DRAM. We want to use that effectively. We also see, and this is where, okay, so those two things were right. This is where missed the mark slightly. One of the things that they were really designing for was the presence of non-volatile main memory, which back in 2001, I would have thought surely by 2014, like you just came back from 2014? Wow, how's the non-volatile main memory? It's like, what are you fucking talking about? No, it's like you're so pathetic. It's never going to happen. I would love to see non-volatile main memory. I don't know if we're ever going to see it. But the ZFS was also kind of designed with that in mind. But so there are these big trends that ZFS was designed around, blew up the volume management divide, and now you've got one cloud, effectively, where you plug disks into the bottom, and you have file systems plugging into the top. Because a file system really is only an administrative nexus. It shouldn't be anything more than that. So you should be able, there should be no real, a file system is just, it is a path, it is hierarchy, and it is policy. That's it. That's all a file system should be. A file system shouldn't have any direct one-to-one association with a disk, lie or not. So in the ZFS model, you just ZFS create a file system. I mean, there's no, you don't have to have a corresponding disk. Similarly, we've got multiple RAID policies. You can have mirroring, RAID-Z2, Del Perry RAID, and so on, and that's been added to over time. And that allows you to solve a whole bunch of manageability problems. And you can deal, because ZFS, one of the great things about it is because it's a totally copy on write design, you don't have an on-disk consistency check. There is no FSCK for ZFS. Such a thing doesn't make sense. ZFS is always consistent on disk. And actually one of the things that they've kind of interesting is dealing with pathologically lying devices, because you are only as consistent on disk as ultimately the device tells you are. And so one of the things that ZFS has added over the years is the ability to roll pools back transaction by transaction until you get to one that the disk was actually not lying about. I mean, if the disk lies all the time, if the disk is the actual enemy, you actually are fucked. I mean, there's nothing that any body of software can do about it. But you can at least, get for those disks that are in that kind of that gray area that appear to be enemy action, but sometimes store the correct data. Say the Western Digital green drives. ZFS has actually evolved to be able to always be consistent on disk, and not require FSCK. Because the thing that they saw is that with data sizes climbing, it's like you can't, or I guess Hacker News did try for the 36 hours that were down. You shouldn't try to FSCK a terabyte. That's not a rational thing to go do, because the I/O speeds of spindles have not fundamentally changed. IBM RAMAC is a 1200 RPM device. Most spindles today are 7200 RPM devices. You have some 10K, some 15K. Then you've got SSDs, which are their own topic of conversation. But that's amazing to me, that you've gone from 1200 RPM to 7200 RPM. In 50 years. So that's not, the performance is not substantively different. So a terabyte is a lot more storage than we had in 1956, but actually doing random reads from it is actually not materially faster. It's like 4x faster than it was in 1956. That should be terrifying to you. And what that means is you can't go back and just read all your data to check the consistency of your file system. That should be something that does not exist. It doesn't exist in ZFS. ZFS also, by nature of the fact that it kind of owns the whole stack, ZFS checksums every block, but it checksums every block indirectly, which is something you can't do when you've got this volume management file system divide. So it knows when it pulls a block off of the disk, it knows what the checksum for that block is supposed to be, not because the checksum is stored in the block, but because the checksum is stored in the block that points to that block. So it knows when it's got the wrong data. I would be like, hey, you firmware, that's the wrong one. I caught you. No, don't give me that one, you asshole. If you mirror, ZFS will actually heal your data. So ZFS, if you get the wrong data off of one half of the mirror, ZFS will write the good half, the good copy over it, and you get these errors. Early in ZFS's life, we would see these checksum errors come out of ZFS, and it would tell you, don't worry, I had some checksum errors, but it's cool, like I got the right data. And you're like, okay, that's obviously wrong, because we are running on, and you can pick your vendor, you can pick your controller. We had one where it's like we were getting really persistent checksum errors from every instance of a particular controller that was like, there was like 6 million of these in existence. And you're just like, this controller can't be this broken. It's just not possible. As it turns out, it was that broken. And there was a bug, a silicon bug in the DMA engine. And it just under certain conditions that were actually relatively reproducible, it just wouldn't DMA the last 64 bytes of a block. Just didn't feel like it. And God only knows how many life support systems suddenly clicked off because the last 64 bytes was missing from these payloads. And we would see this across the board. What was great is, and this again happened early in ZFS's life, it's not as amusing now because people now trust ZFS as opposed to whatever they're deployed on. But you get no, ZFS has to be wrong because I spent so much money on SAN X. It can't be wrong. It's like, well, funny story. It actually is wrong. So, and these guys get it wrong. It's because it's hard. Is the reason they get it wrong. But ZFS has been, again, over the years, we've gotten to the point where we've got absolute data reliability. One thing I would say, by the way, and this is true, this should be true for any system that is designed around safety and integrity. ZFS never went through an era where it was unsafe or didn't have integrity, or people lost data. It's kind of amazing to me how much in software people are willing to write off software that does this as kind of pubescence. It's like, yeah, I lost my data, but a million eyeballs, it's getting better all the time. It's like, no. This is like a 12-year-old who's stealing cars. This is an issue. This is not well, he's only 12. It's like, no, he stole a car at gunpoint, having just robbed a liquor store. You've got an issue here. This is not, you can't just be well, call me when he's 18. It's like, yeah, you want to see what this guy's like when he's 18? And so this whole idea of better if I lost my data, but yeah, I'll come back tomorrow. It's like, no. There are things that are wrong by architecture. You should not. And ZFS was architected to be reliable in terms of data. So, and that's kind of and we can go into lots and lots of depth on ZFS. In terms of my own personal history at Sun, we had developed ZFS in 2006. I and a bunch of coworkers wanted to go and actually build an enterprise storage product around ZFS. So that's what we did. And we We regrettably succeeded, and unfortunately, one of our biggest early customers was actually a customer that we hadn't sold a lot of gear to in a long time. This database company you might have heard of, sadly, I think that there is at least to a certain degree, they're like, oh wow, like you guys are making interesting things again. Whomp! We were actually. I thank you. I have that daily affirmation. I still feel like I've got survivor's guilt. I just feel like there's more I could have done. But so we built this storage product based on ZFS, and building a storage product, by the way, and I say this having gone into this with what I thought were kind of eyes open in 2006 when we started doing this. Building a storage product is like going backpacking in Afghanistan. And if you don't think you're going to a war zone, you're delusional. And so we were like, oh, I think this will be like, we'll make an enterprise storage product and it'll be great. And we learned a lot, and we improved ZFS a lot actually as a result. The ZFS that you have today is a ZFS that's done a couple of gritty tours of duty in the enterprise storage wars, because what you learn in doing that is the number of ways that storage can fail. Because going into it, I was like, okay, I got it. Like phantom reads, phantom writes, bit rot, like all good. Sounds good. Oh boy, no. The firmware is so many steps ahead of you in terms of its creativity and the level of Byzantine failures. Because firmware is like, really, you think that's all I got? We had a firmware bug. This is where I can start rattling off. This is where actually I need to rattle off. My therapist says I need to talk about the firmware revision numbers just to let it out. It'll corrode me. So the Seagate SU0D firmware had a beautiful bug in it where there was a software bug on the head where it misapplied, the polarity was wrong. On the head, it's like, it's like good polarity, head. It seems like that's important. It's like, it is important, yes. And when you got to certain LBAs, got to certain logical block addresses, instead of decelerating the head, it would accelerate the head into the cylinder. And something on the disk, some JTAG or something was like, oh, no, you don't mean that. You don't mean that. No, this will actually, there'll be smoke coming out of that if you do that. So it would actually power cycle the device. It would power cycle the drive. So, and it would bounce the drive. Well, how long does it take the drive to bounce, come back up, and start serving IOs? About 650 milliseconds. So you start seeing these IO outliers at 650 milliseconds. You're like, what the fuck is that? And ZFS is not designed, at the time I should say, I think this is the major difference between a file system that works, that you trust, and one that has actually runs hundreds of thousands of spindles in enterprise storage, is the ability to sort out these kinds of failures. Because ZFS would go on a long vacation when it would hit these kind of spindles. And it would be like, because the problem is the IO would because it was effectively a race condition at the head, the IO could succeed. And because the IO could succeed, ZFS would kind of drag on. Well, the whole array would grind down. Doing things like big snapshot deletion, doing things like, if you were using ZFS back in the day, if you had a gigantic snapshot and deleted it, we would be doing a bunch of random read from the context of a transaction, which would as I said, at Fishworks, we never lost anyone's data, but it went on some very, very, very long vacations. And it was like, oh, Lassie, come home. And the thing is, like, you could be on the machine and you could see, like, you can actually kind of like, you're using dtrace to like watch its progress. And you're just like, I actually have one customer just like, okay, like I'm figuring out the progress. Like, okay, I know when this is going to be done, when this transaction group will be synced out. Let's see, today it is Monday. And it literally is going to be like, by Thursday at 8 p.m. it'll be done. And he's like, yeah, fortunately, I don't care about the data on this system, so let's just throw this one overboard and start over. But we repaired all those things. And this is kind of what we did over those years is we got the system to be so resilient in terms of those kinds of failures. Then the Nazis invaded. I fled. For a while, I tried to not go to Nazi allegory when talking about Oracle, but I actually think that it does a disservice to not go to Nazi allegory, because if I don't use Nazi allegory when referring to Oracle, there's some critical understanding that I have left on the table. There's an element of the story that you can't possibly understand. In fact, as I said before, and I emphatically believe that if you had to explain the Nazis to someone who had never heard of World War II but was an Oracle customer, there's a very good chance that you would actually explain the Nazis in Oracle allegory. So it's like, really, wow, like a whole country? Yes, Larry Ellison has an entire country. Oh my God, the humanity, the license audits. Yeah, I should talk to Poland about it. It was bad, bad. It was a blitzkrieg license audit. Anyway, and after that whole thing, I left. And actually, I went into Oracle. This is stupid. I went into Oracle with this like stupidly. I just want to go back with the time machine and punch myself in the mouth. If we invent a time machine, the first thing I want to do is go back to myself and just deck myself circa 2010, because I was like, oh, it'll be great. Like, Oracle understands business and Sun understands technology, and it'll be like a business that understands technology, man. It's like, are you stupid? It wasn't that at all, and that's not what Oracle is at all. They're a monopolist. They're not, anyway, whatever. You can go see a full uncensored history if you Google Fork Lumos. The funny thing actually about this talk is that I gave this talk, which was at Usenix, at a conference that turns out Oracle sponsored. And the conference was a little concerned about some of my candor. And I, by the way, did not mention the Nazis in that talk. I did not say that at all. But there were a couple other things I did say. But I knew that Oracle doesn't care, because the thing is, Oracle's a sociopath. They don't care what trust me, that Oracle does not care what I think about them, or what anybody thinks about them. But the conference organizers were very concerned what Oracle would think. And so when the videos for this conference were all made available, every video came up except for mine. And I believe in incompetence over malice almost always. So I'm just like, all right, well, someone just like lost the file or whatever. I don't know. They haven't gotten around to it. But like a week passes, 2 week passes, and finally it's like, wait, where is the video? Why is every other video for every other talk up except for mine? And then finally my video appears. You're like, oh, okay. And you go watch it, like, oh, this is a big disclaimer that has never been on any other Usenix video. The following views do not represent the views of the Usenix Association, And you're like, all right, you wieners. Fine. And then you go into the talk, and the format of the talk is like, you've got the slide, and you got like my little talking head down here, and the slide here, and there's like this black strip above my head on the video. And they took this disclaimer and like mashed it up, and it's above my head the entire time I'm speaking. They did not bleep me out. So that is obviously, I'm glad you asked, because that is clearly the next peak that I need to conquer. I actually need to try to get actually censored. I did think that they should start like flashing it when I started getting really colorful about Oracle. But anyway, you can go watch that talk in all of its uncensored glory. But so, moved on. I came to Joyent, and a lot of us went to a bunch of different places, but a bunch of folks came to Joyent. For us, for Joyent, and Joyent was actually, long before I was at Joyent, Joyent was the first user of ZFS outside of Sun. So the first production user of ZFS was Joyent in 2005. And so we'd worked very closely with the founders of the company, and I was excited to go work there. And so for us, ZFS is really the core of what we do. We are an infrastructure as a service cloud provider that also makes available our software stack to run private clouds. Okay, so we had great infrastructure as a service, but the thing that we were missing was object storage, S3, right? So people use S3, you know about S3, right? So this is, have more people really heard of ZFS and S3? I assume you're just like not raising your hand because like obviously everyone knows about S3. I'm not. We're ashamed. Oh, ashamed. That's it. There you go. That's right. Very good. So S3, for those who don't know, is the simple storage service. This is really the first cloud service to give Amazon their propers. This is the first cloud service. It is a storage service, an HTTP-based storage service. And S3 did something very, very, very important. S3 did not do what, frankly, I would have done and a lot of other people would have done at the time, which would be to take an existing file-like abstraction and make it available over HTTP. That's not what they did. It is an object store, not a file store. So in particular, you cannot do partial writes to an S3 object. And that is really, really important, because when you say, I would have guessed that like, no, you can't just not allow partial writes, like, won't that not be acceptable? But as it turns out, that's actually acceptable, because there's a lot of data out there that is write once, read many. And you've got these objects that are logs or whatever. You're not mutating the middle of your log. You're not mutating the middle of your web assets. You're not mutating the middle of your backup. In fact, you don't want to do that. So the fact that it was object storage was valuable. And so that was actually extremely important. because that changed the constraints of the system, allowed them to build a distributed system. And we historically have not had an S3. So we don't have S3. And it has been the kind of the glaring gap, the gaping hole in our offering from our perspective, so we didn't have this object storage. And so the question that we had is, can we build something interesting out of ZFS? So I just kind of come through this backpacking trip to Afghanistan with ZFS, and I'm thinking, what can we go do with ZFS? What can we do with ZFS or send receive? What can we go do to make it easier to implement object storage? And I couldn't come up with anything. Or the stuff I came up with was just terrible, obviously. So, all right, let's put that aside. And I want to talk about virtualization in the cloud for a little bit. And I promise we'll come back to ZFS in a second. So, virtualization is absolutely essential to the cloud. Virtualization is all about allowing multiple tenancies, allowing multiple tenants on a single system, giving multiple people the illusion that they have an entire system, and allowing them to be on there securely. You need virtualization to be able to do that. And the question is, where do you virtualize in the stack? Because you actually have a couple of choices. And the historical answer, since the 60s, is hardware-based virtualization. So we started in the 80s, now we're back to the 60s. Actually, I can't go much further back than I guess the RAM Act is as far back as you're going to go. But and actually, it's kind of interesting how this was born. Hardware virtualization was born with the introduction of the IBM 360. So the IBM 360, introduced in the mid 60s, probably the most important single computer that was ever introduced, because it combined IBM's commercial and scientific lines into a single microprocessor, into a single system, the 360. One of the systems that they left behind was the IBM 1401. The IBM 1401 was an accounting machine. It was one of these things that people were using as a computer, but it existed in this gray of twilight of early computing. And certainly you had programs on it. I mean, it was a stored program computer, but it was not appropriate for scientific calculation. The 360 didn't run any 1401 programs, because fuck that. And like, if you want software for this thing, like, write some. That was literally the logic in the 60s. That hardware is the tough stuff. And so, like, if you want some software, get writing. I don't know, you'll find some people, and there's the instruction set architecture, and go to town. Well, the thing that's amazing to me is that even by the mid-60s, that was an unacceptable answer. And because people had IBM 1401s, and that they were running software on, and they wanted to go deploy it on the 360, but they didn't want to rewrite that software. IBM, classic in kind of classic, tale of the industry fashion, IBM is like, well, no, fuck that, we're just not going to do it. So Honeywell, who was a competitor of IBM, said, actually, why don't we go do that? And so they did the Honeywell H200, which was bit for bit compatible with the 1401. All of a sudden, that thing starts selling like hotcakes, because everyone is replacing their 1401 and their 1410s with Honeywell H200s, not with the IBM 360. Well, suddenly, you got IBM's undivided attention. And what IBM did, going back to remember that earlier theme, the persistent theme of computing, it's lie time. And it's time to lie to that software and tell it that it's on an IBM 1401. We are going to create an IBM 1401 strictly out of software. It's going to be a pure software construct, and it will be so persuasive and convincing that the 1401 software running on top of it will have no idea that it is in fact not running on a 1401, but a 360. And we have this theme has carried through the day. When you run on Amazon, your operating system kernel that you are running on AWS is absolutely convinced that it's running on hardware. It's a statement that is somewhat true, but it's not completely true. The thing that's actually an amazing little footnote on this one actually is I was actually out here in New York after the Y2K rollover, and I was talking to a CIO from a very big bank out here, and we're just kind of shooting the shit about Y2K, which is obviously a big fizzle. For us at Sun, about 30% of our Y2K problems were actually leap year problems. I don't know if anyone else had these. So recall that every 4 years is a leap year, except for every 100, except for every 400. And there's a stunning amount of software that managed to encode rules 1 and 2 and not rule 3. Because 2000, of course, 400 divides 2000 evenly. 2000 is a leap year, despite the fact that it divides 100, that 100 divides it evenly. So anyway, whatever. So we had a bunch of those bugs, who cares? And so, and he said, it's funny, in terms of Y2K problems, all of our Y2K problems, or the plurality, 45%, something like that, came from a single hardware platform. I was just like, yes? What? What is it? And he had good kind of like good dramatic pausing and pacing. I mean, I was going to pee my pants. Like, what is it? What is it? What is it? What is it? The IBM 1401. And it was like, I mean, I was like, the who's he, what's he? The same IBM 1401 that was last made in 1963. It's like, the very same. It's like, well, he's like, oh yeah. Yeah, and apparently this kind of caught everybody by surprise. Everyone was like, wow, okay. And clearly, like, this is not like running the exchange or anything. I mean, this is clearly running in very, well, it's not to the best of my knowledge. This is clearly running kind of ancillary components, but it was there and it was real. And like the Y2K solution, but this is where like Honeywell H200 may have bought the 1401 some life. But ultimately, like the Y2K solution for the IBM 1401 actually is write some new software. They're actually, the 2 digits of the date are actually enshrined in the hardware, so you're kind of boned. But to me, and that was an amazing moment to me because I think it tells us about the persistence of software. That here you have software that is written in the late 50s, early 60s, maybe as late as the late 60s, but not the 70s. By the 70s, this is an antique, this machine. And yet it has survived the death of not only that hardware, but the hardware that replaced it, and probably the hardware that replaced it. It is running virtualized, and virtualized, and virtualized, and it was running on a Z machine. It was just like, whoa, amazing. I mean, I think I was like staggering around for an hour after that. But it's amazing. So that is certainly the oldest answer to this question, and it's still a valid answer, is to virtualize the hardware. But the problem is that, it's this theme again. The lie works great at first, but then you begin to pull things and the lie begins to snap. In particular, when you are virtualizing the hardware, similarly to when you are virtualizing the device, the disk, when you're virtualizing the hardware, the semantics that you have are very narrow. In particular, like take DRAM. If you have virtual hardware, and I'm going to give you virtual hardware, I give you a certain amount of DRAM. I give you a gig of DRAM. I have to really give you that gig of DRAM. I can't really lie about that. I can try to lie about that, but the operating system really thinks that it has a gig of DRAM, and it's got the right to think that. And I can't make DRAM show up later. The operating system is not like, what is, there's another DIMM over here that I didn't see? Like, what's this thing? You definitely can't take DRAM away. So when you have, in terms of the number of VMs that you can reasonably put on a machine, take your DRAM and divide. And yes, you can if you're a crooked service provider, you can oversell your DRAM, and maybe that will last enough for you to sell the business and move to a remote island. But that basically doesn't work. You can't really oversell the DRAM because the operating system very much believes it has DRAM there. And this is true of CPU. It's true especially of I/O, networking I/O. You're basically just boned on networking I/O. There's not a way to make that efficient because you're going to have to get out and talk to there are tricks you can pull, but the tricks that are pulled that are effective are actually taking the hardware and taking it straight into the guest. So it's like, well, it's not really hardware virtualization anymore, is it? It's like, oh, we won't tell the lie. Like, this lie will happen to be the truth. And now it performs. It's like, yeah, but now we're getting all the advantages of the lie we're losing because we're not actually virtualized. So there are lots of problems with hardware-based virtualization. There are lots of advantages too. Namely, I can run my old stack completely. So we have, in the joint public cloud, we've got hardware-based virtualization via KVM, but we also have, brief segue to platform-level virtualization. Doesn't work. So the platform, you can virtualize very high in the stack. The problem with doing that is you end up with what they call the Google App Engine problem, where you're so high in the stack that you can't actually develop big apps. That when something gets big, it has to move somewhere else. When something and all PaaSes have this problem, but by then they've usually gone out of business because this is a terrible, terrible, terrible business model. So our solution is OS level virtualization. So OS level virtualization is where I've got one OS kernel sitting on the hardware, and I'm going to punch out multiple containers. And these containers are going to look, feel, and smell like their own operating system, like their own hardware even. I can reboot them. But they're actually not their own hardware. The level of the abstraction going up to this thing is not the hardware. The abstraction is the system call table. And as a result, it's sitting on the hardware. It is running on the hardware. it sees all the CPUs. It sees all the DRAM. Now, you may only allow it to only allocate, say, a gig of DRAM. But when you give a virtual OS a gig of DRAM, all you're doing is writing down somewhere, hey, like, by the way, like, this guy hits a gig of DRAM, cut him off. That's all you're doing. And if you want to, so if you are deployed in the joint public cloud and you want to resize an instance, you just go resize it. And we just say, oh, okay, all right, make that 2 gigs, I guess. Okay, make it 4 gigs. I mean, provided that we're not overselling the box, we can always resize DRAM up and down, which is very nice. And there are lots of other great attributes of this. It performs very well, and so on. And we've got we've got zones in SmartOS, which is a really bulletproof implementation of this. And I think it's been great to see. I have to say, this model, I've been so convinced about this model that people have asked, like, well, how do you guys feel about like Docker and LXC and so on? To me, it is very validating to see that, because I think what I see other people seeing in Docker and LXC is the power of the model. And I think the model is the right model. So I'm glad that those technologies exist. And then I'm especially glad that, at least in LXC's case, they exist, but they're flawed. So definitely, deploy on LXC, and then if you want to have zero security problems, you can actually deploy on Sonos. Sorry, that was. I was really kind of fixated on that kind of the ZFS side of this when you go back to object storage. And I hired this guy from Amazon, Mark Cabbage, who's a senior guy at AWS. And he and I were kind of mulling about this problem about how we develop this kind of object store, and I just could not stop thinking about ZFS. And he had the key insight, which is actually it's not about ZFS, Dumbo. It's about OS level virtualization. Because what OS level virtualization allows us to do is build an object store, a la S3, HTTP facing object store, put, get. But if I want to actually do anything to those objects, if I want to compute on those objects, if I want to do something besides just retrieve them, instead of having to get it and then run something on it, instead of having to get it and grep, say, I can actually just spin up a zone, spin up a container where that object lives, and grep right where the object lives, without actually moving the object. It's like, oh. It's like, fuck, why did I not think of that? And in fact, what was funny is when I was kind of going back and thinking about this is such a kind of a moment where you're just like, wow, especially for me, like I've been, living these technologies for decades. It's like, how can I not see this? But sometimes, oftentimes, these big insights they actually, they seem simple only in hindsight. These big insights actually require really a great insight. And the thing that was funny is, I remember vividly where I was when Jeff first described ZFS to me. I was in my poorly lit office circa 1999. So I remember that vividly. I remember vividly where I was when I first described dtrace to Jeff, when I interviewed at Sun. I remember, but I could not remember for the life of me where I was physically when Mark told me about the idea that would become Manta. And he couldn't remember it either. Well, no, actually, he remembered it incorrectly. It's like, I'm pretty sure, weren't we together at a bar or something? Like, no, that's wrong. I would remember that. And so we went back through IM logs trying to figure out, maybe we can just find the first time we were referring to it and then go backwards. And then I realized the reason I couldn't remember where I was. He told me over IM. So this is the actual sound of my brain detonating. We have recorded for posterity on the 24th of October, 2011. Okay, so you've got the crazy idea. We escalate now produce for first-class citizen by way of routing your JS code to some node thing running on a separate zone on the same place as your data, which is not exactly what I said, but it was kind of obvious what the next step is. I was not sure if this would be viable or not. And I'm like, fuck, that's a good idea. And then I just, I really was not raised this way, but I do kind of talk like a sailor over here. Apparently this is the highest praise I can offer is to call someone a fucker for coming up with a good idea, which is really an inappropriate thing to say to someone who's just had a great breakthrough idea. It's like, earlier you've been asking about Ackles cross zone and CFS. And then of course you just get why did I think of that? So it's a great idea. It's a really, really, really good idea. And so we built it. That was October 24th of 2011. And we spent all of 2012 actually building this thing because you can't, it's unfortunately, wishing doesn't make it so. So there's actually a pretty sophisticated distributed system you have to build on top of this thing. I mean, yes, we use ZFS as the fundamental local storage underpinning. We use zones fundamentally, but we had to go build a big distributed system on top of it. And as we were building it, what was becoming clear is that, like, wow, what we've actually done here is we are actually leveraging the Unix tool set to be able to go do this kind of ad hoc data processing. And I would like to think of myself as an acolyte in the Church of Unix. So I think you begin to see the kind of historical context of that. And for that, we're going to go back in time just quickly again. I assume you all know about Unix. It turns out sometimes I have to remind people that Linux did not invent some of these abstractions. They actually predated it, but it's a good Unix system. But Unix first appeared in the 1970s. And Unix was actually a play on Multics. Multics was the system that actually predated Unix. Multics, by the way, created the // if you're curious, among other things. And one of the best things that happened in history is the Multics system that was running at Bell Labs, running the GE635, that was taken away from them. And they had used Multics and they enjoyed it, although they thought it was a big, cumbersome system, and now it was gone. And so they wanted to go build something of their own. And so what they actually did, the funny thing is, and as Dennis Ritchie says, we were a bit oppressed by the big system mentality. Of course, it was the 70s too, and they were all kind of hippies, so there's that too. And Ken wanted to do something simple. The thing that's kind of interesting, actually, is that the first, I mentioned it there, that the first programs actually were designed to test the file system. That's actually what they actually implemented, was a file system. And these commands were basically throwaway commands to just verify that the file system was working. Commands that many of you have typed today. You're using test-driven development from before you were born, for most of you. Before I was born, or when you were very, very young. So and Unix, the thing that's kind of interesting is that the Unix philosophy did not only start with Unix. The Unix philosophy really started with Doug McIlroy. So I don't know if people know who Doug McIlroy is. Doug McIlroy is and Doug McIlroy, you think of Ken Thompson, Dennis Ritchie as being the inventors of Unix. You really need to put Doug McIlroy rather, in that pantheon. And the reason for that is because it was McIlroy's idea that is the thing that we most associate with Unix. And that is the actual ability to pipe the output of one command into the input of another. And the thing that is funny, talk about like the simplicity sometimes not being obvious. This was obvious to McIlroy in 1969. This is 2 years before Unix, and he called them, I think, hoses. It took him 3 years to persuade Thomson to implement it. He's literally like in the next office. And to kind of read the history on this, it sounds like there was like a daily kind of beating. And finally, the big breakthrough was McIlroy comes up with a syntax that made it clean in terms of piping it. That syntax, by the way, was not the pipe character. I don't know if people know what the syntax was. It was the caret. Yeah, it was the circumflex. Very good. The true old schooler. But so the pipe came very shortly thereafter. And then Ken said, I'm going to do it. And of course, it took him a night, which is like the classic thing in software. It's like, you spent 3 years telling me this is technically impossible, and then you do it in a day. It's like, technically impossible means I really, really, really don't feel like it. And then I love this. This is like the book of Genesis. I mean, this is... To me, I mean, talk about like let there be light. And the next morning we had this orgy of one-liners. It's like, unfortunately, I don't actually know that we know what morning that was. And actually, the thing that's funny is that I think one-liners have always been kind of very important to me because you're got all this syntactic power that you're putting in one line that you can kind of understand. And I think any system that results in an orgy of one-liners is onto something. And certainly, and this is kind of the example of that. But truly, the kind of Unix was born, I think, that morning. And that gave rise to the Unix philosophy. And this is verbatim the way McIlroy talks about the Unix philosophy. Write programs that do one thing and do it well. Write programs to work together. Write programs that handle text streams, because that is a universal interface. So that is, I believe, the most important philosophy in systems development. I think that we should all apply this to everything that we do. The way we are able to develop complicated systems is by building them out of simple ones, taking simple systems and connecting them in interesting and new ways. And the way you're able to do that is by having programs that do one thing and they do it well. And I think that, by the way, not everyone believes this. So there's a bit of a tension, I think, between, and as the older I get, the more I kind of view it as a holy war between the forces of complexity and the forces of simplicity. The forces making these big, complicated, for lack of a better word, and I'm sorry if I offend anybody, but I think it is a framework-centric view versus a library-centric view. The library-centric view says, hey, I'm going to come up and I got a bunch of toolboxes for you. Got a bunch of tools. You can use them however you want to use them. The framework's point of view says, okay, you pop into existence in this crazy-ass context where, here are the things you can kind of do. It's like, well, where am I? It's like, well, no, you fell through a black hole. You just kind of wake up here. You're like, okay, all right, well, and you're kind of in this, you're kind of like suspended in space. And I think it makes it very hard to reason about the system when you are implementing in terms of a framework. And I don't want to imply that frameworks don't have a place. They do. But I think when you can build from things in terms of the Unix philosophy, you always should. And I think that this is really the most important revolution in software thinking. This gives rise to what I call the epic rap battle of computer science history. So I had this knee injury earlier in the year, and I ended up on my back for basically 4 weeks. And I think I watched the entire fucking internet. But if you've ever seen the epic rap battles, they're really very funny. And like Darth Vader versus Hitler is a particularly good one. I think it's like Tom Siebel versus Larry Ellison or whatever. But the one for computer science is John Bentley, Programming Pearls, and he poses this problem. Read a file of text, determine the n most frequently used words, and print out a sorted list of those words along with their frequencies. The amazing thing about this challenge in 1986 is that this is probably an interview question for an intern, right? I mean, this is a question of have you played around with Unix for a couple of months? Is basically, that is what that question is. People saw that, I thought it kind of neat, the CLI mystery on GitHub, where you solve this little mystery by using basic CLI tools. I think which is cool. It introduces people to the power of this. But you would expect someone who's able to do that to be able to do this. Don Knuth's solution, the great Don Knuth, who love, obviously Don Knuth, one of the fathers of computer science, but his solution to this was an elaborate program in this new system, of course, called Web. And since you haven't heard of it for a reason, it's a Pascal, this is the whole literate programming thing, which is okay, Don Knuth, a lot of very good ideas, some stinkers, literate programming, I'm going to put in the stinker pile, what have you. 7 pages of dense algorithm for this problem. And then, like Indiana Jones pulling a pistol, Doug McIlroy has this solution. And the amazing thing is that in 1986, the performance was nearly identical. The performance difference was almost the same. And now, you're very hard pressed to beat this. This performs really, really well. This performs really well because these are simple tools doing one thing. One thing is that you might. So this is, TR translates characters from this is going from uppercase to lowercase. And you can kind of see all the things that it's doing here, sorting, uniquely minus C, sorting minus RN. And then I think this is kind of funny. And then the sed over here to give you, if assume that the top n, the n that you want, is stored in $1, we're doing a sed $1q, which is the equivalent of head. They're just doing a head minus 10 or whatever. Well, why the hell didn't you use head? It's 1986. Head was not in AT&T Unix in 1986. Isn't that amazing? I was actually stunned by it. I had to go back and check, but sure enough, head was actually the head tail, but not head. So go figure. Anyway, so what we're seeing with big data is that history is repeating itself. So remember that Bentley challenge. Here is the challenge verbatim from the MapReduce paper, from the Dean paper. So the count URL access frequency. Function processes logs of web page requests and outputs at tuple URL, 1. The reduce function adds together all values in the same URL, emits a URL total count pair. Wow, that sounds a lot like Bentley's challenge. But the solutions do not adhere to the Unix philosophy. The solutions give the Unix philosophy a night that never forgets. The solutions are really a desecration of the Unix philosophy. And in particular, they've got an appendix that has, and it's like 150 lines of C++. The kind of C++ that's been like really heavily edited down to just jam into 150 lines to do just this. Then right, there's a 71-line word count. Word count. An idea that's so old that the command to implement in Unix is 2 characters, WC. If you want to do a word count, if you want to do a word count of a document, your first instinct is like, okay, I need a C++ compiler. It's like, what? Wait, are you one of the framework people? How did you get in here? It's like, no, you have WC. Well, why is it that when I do a word count on my laptop, it's WC, but when I do a word count against my logs in the cloud, it's all of a sudden it's C++ and it's Java and it's Hadoop. It's just wrong. So what Manta allows us to do is, and this is actually verbatim Bentley's challenge. You can cut and paste that. In fact, we'll do that in just a second. And run this in terms of Manta. So what this is doing, let me actually go kind of run some of these things, give you just a flavor for what, what Manta looks like here. So let's see, people see that, I hope. So all of the Manta commands, of course, because we are borrowing from Unix and Multics before it, one of the differences between Manta, which is the system that we developed, it's an object store that has compute as a first-class operation. The difference between Manta and S3 is that we have true hierarchical storage. So S3 is not hierarchical. If you've used S3, it's a key value store. It's one that violates a bit of a gentleman's agreement in that it accepts the / as a character. So you create, I'm going to create foo/bar/baz, and S3 it's like, okay. And it creates that. You're like, okay, now I want to create, foo/bar/bop. And now I want to let me go see what's under foo/bar. It's like, oh, no, that's not the way I work, really. It's like, well, why did you take the /? It's like, I don't know, you wanted a /. So that's not, I think that I think if they were redoing S3 today, they would make it hierarchical because it's too difficult otherwise. But Manta is hierarchical, and I'm just going to list my public directory. So bcantrell public. So what that did, and you can see that's, well, you can see 2 things. One, I have a bunch of crap in my home directory because some things never actually change. But 2, you can see that is actually, yes?
While you're typing this stuff, is it actually going up?
Yes. And actually it's great. I love being on the East Coast. I'm so close to Ashburn. Like when I'm running this now, I'm like, wow, that's a rocket. And I mean, it's fast on the West Coast too, but it is really fast here. So yeah, I mean, you're right to ask. And I actually was kind of like, wow, they said actually like that's going over the internet, right? Because we are so close to Ashburn here. So Manta's all in US East. And that whole speed of light thing, there's a lot of truth to it, so as it turns out. Now, see, this is why I should do a list of my home directory. What is Manta prawn that that we're not going to open. I'm smart enough not to open that. But so, so you can see that it is super fast, and I can actually go do. I can actually ls these things as directories, and in fact, people have written. This is I'm going into I think these are all the This is the V7. Took all the V7 stuff and uploaded to my public just to give you kind of a bunch of files. And we got the kind of things you would expect. So I can do like an mfind of bcantrell public v7, and that did a find of that directory. And so these are all a bunch of objects that are under that directory. So if I wanted to actually get one of these, I could I don't know. Let's go to is it userman? They don't have a, let's see, we'll get one of these. Let's mget, what the hell is what is pecan? Why, Unix, why are there still, pecan, established packet protocol. All right. Okay, this was a thing apparently. Yeah, so that's actually, and that actually should be able to, this might work. that work? Oh my God. So talk about that was like a man page time machine I just did. I literally extracted a man page from like the mid 70s and rendered it on my local NROF on my local Mac. So wow, okay, that it all worked. But and they even have a less than sign in like UTF-8 or whatever. Man, they are on it. Okay, well, whatever. That's an object. I use mget to get it. Obviously, this is a small object, but it could be a terabyte. We don't limit you on object size. You can stream if you have to do with big objects in S3. If you don't have to do with big objects in S3, you don't care about this. If you do, your life is a living hell because of the multi-part upload business and the way you have to chunk these things in. For us, you just stream. So you just open and just pound us with data. If it's more than 5 gigs, you just need to tell us in advance how much we should expect so we can go stream you right onto a machine that's got enough storage for you. That's it. But other than that, it just works. So there's an input, and you can input a file, you can pipe to input, mget, and so on. And we can kick off an M job, a Mantha job, and so let's actually go do that. And then I can kind of show you what this thing does. So I'm going to bring up a new window over here, and I'm just going to literally cut and paste that. So, but I'm not going to do the set. I can't force myself to type the stupid sed thing. I'm just going to do head-10 for that. What that's going to do is find a bunch of objects, and it kicked off a job, and I'm going to let that actually run in the background, so I'll show you what some of those parts look like. So if we do, you saw the mfind, and the mjob create is running that where all those objects live. And to give you kind of a flavor for that, actually, let's go look at some of these objects. And to kind of give you a flavor of what you can do, one of the things that we actually invented is one of the early things that we started using this for is the ability to actually go debug core and crash dumps. So when you debug a core or crash dump, let's see if I've got I've got an example coming up later. When you go to debug a core or crash dump, the dump is this huge kind of thing, and you want to be able to go debug it interactively. It's a great thing for in situ compute because I don't want to move this big dump around. Well, the problem is that I want to debug it interactively, and so I don't want to just have a job that just goes off and greps this and returns. I want to actually I want to log in interactively to the zone that's sitting on this object. And fortunately, I complained about this just loudly enough that Josh Clulo, one of my colleagues at Joyent, invented this thing called mlogin. So what mlogin does is it actually logs in so it's creating a job. I have now logged into the object. Yeah. So if I look at my environment, what I have is Mantha input file is this object. So if I can do a file of Mantha input file, and it will say that file knows that it's TROF or preprocessor output. Ancient history detected. That file is just here, and if I wanted to operate on it, not that, there it is. But I'm actually sitting on the machine. I'm local to the machine. I can't see anything else. So if I look at what's mounted here, what we have done is we can only see, obviously, only my object. And I'm in actually, one of the things that's been kind of amusing, actually had someone tell me, it's like, I love Mantha because you guys finally stopped trying your whole like SmartOS thing. You finally built something that is like soup to nuts Linux. I'm like, what are you talking about? It's like, well, I did an mlogin there, and I'm sitting in Linux, which is great. I'm like, right, yeah, exactly. Well, you know what? We finally, you were right after all these years. The reason they thought that is because if you look at grep, you're getting the GNU grep. If you use tar, we get the GNU tar. We don't give you, we still, and so if you do a which tar actually, it's op local bin tar. If you still want like the ancient tar, it's actually still sitting in user bin. If you want to go back in time, and in fact, actually, all the crazy shit is sitting here. So you've got all sorts of ancient garbage sitting in user bin that you don't use. Actually, this is always an entertaining thing to go do. These are all the 3-letter commands, of which I probably know a third of those. And I'm sure there are at least like 10 commands that no one ever, like BFS, there's a classic. ATQ, what the hell is that? AtQ. Oh, look at that. I can actually display my ad jobs. Thank you, 80s. All right. Actually, what was funny is at was the one of the pieces of software that had the leap year bug. Actually, that good old at. That's the last time at and I crossed paths. There you go. People have used AtQ. That's good. But so you have all the ancient Unix software, but it's actually out of the way in terms of a path perspective. And the software that you actually use is all the GNU software that if you use awk, you're getting GNU awk and so on. So it feels much more familiar. And what you're going to find is that you're able to. And actually, it's amazing when you are. And up here we can see my job finished over here. That this is the answer across those 307 inputs. These are the top words. That is the John Bentley challenge running on Manta. The thing is that most of the time that was spent executing this was actually doing all the bureaucracy of getting to those zones and actually getting those jobs running. This would not run in a materially different amount of time if these things were hundreds of megabytes or gigabyte apiece. Because the data is not moving. The data is sitting on those machines. So what we have found is that this opens up a lot of possibilities. And we are actually busily using Manta to change the way we develop and deliver software. So, I mean, speaking for myself as a software disaster fetishist, the ability to actually keep core dumps in perpetuity, keep crash dumps in perpetuity, and debug them. So we developed a system called Thoth, and Thoth is a system that allows us to using mlogin and so on, where we can actually store every core and crash dump that happens in the public cloud, and constantly analyze them for. And actually, I say every core and crash dump in the public cloud, which actually was my intention. I hadn't really spent much time in the general prison population before. I did turn that on, and all of a sudden, like PHP was basically DOSing my system because that thing core dumps 24/7, 365. And it's like a disk stress test for core dumps. And core dumps in all sorts of wild ways. So we do actually limit it. Like I've got a whitelist. But it's actually very important to me that if you are a public cloud customer, if Ruby core dumps, if Java core dumps, if Erlang core dumps, well, if Erlang core dumps, I'd actually just contemplate ritual suicide if you actually look at an Erlang core dump. But Erlang core dumps are a little bit obtuse. But if those things core dump, I want to understand why. And certainly if we have a crash, an operating system crash, we want to understand why. Now we've got one place where we go to debug all that. We're doing that with logs, we do that with instrumentation. In fact, the Rubicon for Manta was, we have to bill for Manta, sorry. If it were up to me, it would just be free. But we bill, just to get this out of the way, we charge S3 prices for storage. So S3 has set the tone for price for storage, and it's dirt cheap. So it's S3 prices for storage and effectively EC2 prices for your compute, but you only pay for the seconds that you actually run. So if you run a job that takes 10 seconds, then you pay for 10 seconds of compute. And it's 40 microcents per second. I mean, it turns out to be like, you have to do that actually a decent number of times. I mean, you still can do a surprising amount of work though. I mean, if you have 1 million objects, and you run for half an hour on each of those objects, you can all of a sudden the years can go by.
Is that billing resolution for Manta or joint and just normal?
Right now it's joint compute is. I mean, we do that by. I mean, I think we round up to the nearest hour for infrastructure as a service. And if there were, Google made a big deal of getting down to a tighter granularity. We could do it. I don't really. And I found it peculiar. For Manta, it makes a lot of sense. You only want to charge per the second because you create these jobs so transiently. In Google making a big deal out of it, I thought was a bit strange. It's a bit like a hotel making a big deal about the fact that they charge by the hour. It's like, well, out of curiosity, like what kind of clientele is attracted to the by the hour pricing? But I guess. But I mean, for us, it's like, I mean, but an hour of, I mean, it is like. So we do round up to like the nearest 14 cents in the infrastructure for a server side. But actually, I mean, we could charge by the second, actually. We just don't do it because we don't think there's demand for it. But if you want it, actually, we should go do that. We should go, I mean, I think we should probably add up what the differences for all customers in the joint public cloud. My guess is that I've got that number like in my pocket. Anyway. But in order to bill for Manta, billing is such a fucking annoying problem. Right, exactly. It's really regrettable that we have to actually take money in exchange for goods and services. And actually, the way this is done for S3 at Amazon, and the way this is done in a lot of places for this kind of a service is, hey, it's Hadoop time. It's time for a big MapReduce cluster from the mother of all frameworks. And embarrassingly, when we were thinking about it, started thinking about billing, I'm like, oh God, are we gonna have to stand up like a Hadoop cluster for this? And Mark was like, are you stupid? Like, no, you moron. We're gonna use Manta for it. And so we actually Manta uses itself to implement billing. So what Manta does is when you do any requests or what have you, records are stored in Manta. You can actually go to your if I do an MLS of just bcantrell, I will actually get reports, and in those reports I can actually get usage logs. You can log into your bill. You can. Yeah. Yeah. Let's go. Yeah. If you want. Yeah. I mean, if logging into a bill is something that like you get your rocks off on, let's just do it right now. But here we go. It's bill time. Feel the wind in your hair. It's right here. The bill is right here, and you can like print that out in beautiful JSON.
How about deleting it?
Actually you can delete it because this actually bill is like the analog here. The true analog here is Verizon. I don't know what you're talking about because when your bill showed up, I burned it. That's fine. Then you probably don't know how much you owe us so you can torch your bill if you want. This is actually this is a copy of your invoice, and you can actually delete this as you wish. It's only there for your purposes. We got another copy, unfortunately. And then we're one step ahead on that one. But what we do is because this actually the records look the same for us. So we do these big Manta jobs that run on all these JSON payloads, and then we use JSON, which is a tool that a joint engineer Trent Mick wrote, that we put in user bin, but does not date back from SDR3. We use a JSON tool to kind of pick out the particular things that we're interested in, and then the engineer did this originally, did that reduce phase in Node, which is fine. Node does it fine. But we're looking at the code. It's like, this is actually pretty complicated. You could probably replace this with like 5 lines of awk. He was like, awk? Tell me more. And it's like, yes, child. So we had like Sunday school for awk, where we read actually. When I finally go around the bend, I probably will have my own public access channel where I have like the Christian puppets for like introducing awk to, no, baby, use awk. That's actually a very good idea. I think why am I here instead of doing that? Awk Puppet Time Theater. I love Awk Puppet Time Theater. I'm definitely the puppeteer. And so we introduced awk to this young engineer. He's like, oh wow, this is great. And now it's 7 times awk. So now it's just basically Unix command line to do this stuff. That was kind of crossing a Rubicon for Manta when the head started eating the tail. We started actually using Manta to implement itself, and we realized that the power of doing this stuff, because you can build these ad hoc. You don't have to build a MapReduce cluster anymore. You just store your data, and you can do all this ad hoc iteration just the way you do on the Unix command line. So it's extraordinarily powerful. It's very interactive. You've got mlogin. The way we develop these things is we mlog in, and you get your pipeline working just show, and then you come back, and then you create an mjob out of it. Create it on kind of one object. Okay, that works good. Then you kind of pipe in 10 objects. Looks like it's working well, and then you pipe in 1,000 or 10,000 or 1 million or what have you. For us, it's been a real revolution. That's my email. We could do that as well, but that'd be a bit awkward. In terms of the cap trade-offs and a lot more details, I'd be happy I want to let us get to the bar at some point, but I'd be happy to go into details on this. But Dave Pacheco, one of the lead engineers on Manta, has got a terrific blog entry talking about the cap trade-offs. Recall, cap is consistency, availability, partition tolerance. You get to only pick 2 of those. Of course, everyone's like, okay, great, I pick consistency and availability. It's like, no, you have to pick partition tolerance. No. So you are either a CP system or an AP system. For us, we actually split it in terms of reads versus writes. So for writes, we are a CP system. For reads, we are an AP system. What that means is when you do a write, you do a write by default, you can specify the number of copies. By default, you specify 2 copies. They go to Mantas in 2 different data centers sitting in Ashburn, Virginia. Every time the hurricanes start tracking through Ashburn, I guarantee you all of cloud computing gets nervous because like those are the failures that actually aren't supposed to happen. So provided Ashburn does not actually get wiped off the map, you've got 2 data centers that are in 2 different fault domains. And your write will be act back when that object is in both of them. If the object is not in both of them, you will not get act back. You will not get a 200. This is in contrast to S3. S3 will 200 you back when it's written it to enough. And then things will catch up, except when they don't. So if you use S3 a lot, one of the things you may notice is you do a put, 200, get 404. Like, wait a minute. You just told me you put it there. Why, when I get it, are you telling me you can't find it? It's like you do have it, right? And it does show up eventually. And, usually seconds, sometimes minutes, depends on sometimes tens of minutes if AWS is having a bad day. We don't do it that way. You're not going to get, if we can't write to both sides, we know that when data center's down, you'll get a 500 back. Because a 500, we think you know what to do with a 500. Like, we don't have it. Retry later. As opposed to like a 200 that's like a just kidding 200, which is like how the hell are you supposed to do anything with that? On reads, however, if you only need one of those data centers to be able to do those reads. We've got hierarchical storage. You saw that thanks to Multics. We've also got this snap link phenomenon that allows you to affect versioning very easily, CORS headers and so on. The SDK is a node. You can npm install Manta for the command line interface that I was using. I think from our perspective, we believe that the idea that Manta represents, namely bringing compute to data, is absolutely the path forward for big data. The size of data is growing so dramatically. And the size of compute, the actual program text, the awk one-liner, it's like those one-liners are just as true now as they were in McIlroy's day, right? Those are not growing. It does not make sense to backhaul data from object storage in the transient compute. So we believe that, I don't think that Manta is going to be the only system that does this. I'm sure there's going to be some BetterFS LXC knockoff in like 50 years. But which actually be great. In all honesty, I would welcome other systems that have the same model because it would verify that we're not entirely crazy. But we personally believe that ZFS is the only sane storage underpinning for that system. We think that Manta is just the first of these systems. We think we're going to see more. And we're actively using Manta. Manta is changing the way we develop software. So I think that Manta is going to change, we think, the way a lot of people think about big data. It already has in the 6 months that it's been out. Yes?
What are the current constraints around the environment that you can run jobs and log into?
In terms of resource constraints, physical constraints.
It's just environment in general, because there's a pretty sweet conclusion that you can come to when you can log into your storage, because you can start running arbitrary programs.
Yeah, absolutely. So one thing I actually didn't show here, but you can run arbitrary programs. What you can do is you can actually specify that with a job. You don't even need to log into your object to do that. When you create a job, you can give it an asset payload, which is basically a tarball that'll be laid down, and that'll be laid down for you automatically. And so now, and actually, if you want to do R on big data, right? There is no real R system. There are kind of some half-assed kinds of things out there. But you can go do R on big data running at hardware speed. If you wanted to go do Go on big data, if you wanted to go use these things that aren't Java, frankly, on big data, you can now you go use Python for big data. Python. You look at all of these communities. There are, Python in particular. You've got the natural language people have all gravitated to Python, right? And they're all kind of building tooling for one another in Python. If you want to do big data natural language, it's a non-starter to do it in any other language besides Python. Now you can do all that with this.
When you log into an object, how much extra disk space do you have?
Right, that's a great question. So when you create your job, you give it some resource constraints. And as you can imagine, that changes your bill. So by default, And actually, this is why, by default, I think we give you 1 gig, but the easiest way to, so yes, we give you 1 gig by default. So by default, you've got 1 gig. By default, you have, I think we give you 8 gigs or more. I can't remember of storage. I guess I could do, will that tell me? Yeah, 8 gigs, there you go.
That's not really big data.
Well, no, this
I
is,
mean, I work with I pull up objects and data files that are 4 terabytes.
no, sorry, these are, this is only in effectively, this is your mapper. Right, so you've got 4 terabytes. You're going to stream that 4 terabytes through. A gig of physicals is more than enough to stream through. Now, if you where the DRAM, now just a couple things. One, your DRAM is you can size your DRAM to be larger, right? So if you want 64 gigs of DRAM, especially in your reducers, right? Not in your mappers, but where this becomes an issue is when you got a big reducer. We allow you, a la with Hadoop, we allow you to have, and just to show you the way this is specified.
I just feel a little nervous because previously your example of big data was a bag of words, and I'm sorry, I'm a scientist and I work in high throughput sequencing, and it's not a bag of words anymore, honey.
Oh no, I know. And
It's a really funny example, if any other scientist, I don't know who else is a scientist here.
well,
Very
so.
funny example.
Well, we're just like Hello World's not a real program, right? So,
Yeah, but if you want me to take you seriously, you can't use that as an example.
okay. So I actually would recommend it. I mean, if you haven't read the Dean paper, you should, because the Dean paper uses the same examples.
I've
But
read a lot of these papers. I have a PhD in this stuff.
Okay. So yeah, I mean, so if the examples are too small for you, I'm happy to take your arbitrarily sized data. We can go to town because the.
I'll talk to you.
No, we can actually, I mean, we can do demos on terabyte size objects. In terms of, actually DNA in particular, if you're actually looking at sequencing, A's and T's and C's and G's. What's that? Yeah, so that is a total sweet spot for us because in fact, actually, and we've got folks that are currently actually storing. In fact, you should go look at Christopher Hogue, who is currently works at Joyent, but was actually a scientist as of 6 months ago, and started using Manta for his proteomics. And he was enjoying what he was doing so much, and he was kind of sick of science for a lot of good reasons. He's now working at Joyent, and so he's did a lot of the R integration. So if you go look at Chris's stuff, and I can assure, and you and Chris should have a conversation, but I can assure you that we know what big data is. So when I'm looking at
I wasn't saying that.
core
I just thought
questions.
it was a funny example,
Sure. So, but when I mean, but big data for me, admittedly, big data for me tops out at probably about 100 gigs, which is about the biggest kind of crash dump you get. No, 100 gigs for a single object. Well, no, but remember, that's only for a single object. So when you, and I mean, even for you, you wouldn't want your single object. I mean, you can have a terabyte single object, but that's probably overkill. You're limiting the amount of parallelism you can actually get on that thing. And you probably want to frame that object differently. Certainly, if you're in HDFS, you're framing that object at 100 meg boundaries, right? I mean, you think of it as a terabyte object, but it's actually framed at much smaller granularity. So in Manta, the object framing is a much more deliberate design decision. But no, like with Hadoop, certainly other systems, these things scale arbitrarily with data size. So as much data as you've got, you don't have an internet pipe big enough to fill Manta faster than we can accommodate you. I can guarantee you. What's that?
Just have an example just for the asshole scientist in the back. Just so if there's an asshole scientist in the back, just be assured you can still do your sequencing analysis.
Be assured you can still do your sequencing. Yes.
Small note.
I have a question about billing, actually.
Yeah.
I'm doing the math, and I'm really bad at math. And
Was-
some projects or some specific workloads, like 40, 50 gig gene sequences, running really complicated things. That
Okay.
Take a week or so. And I did the math for a week of compute time with 8 gig RAM. It's going to be $150 for one project for one workload.
Yeah, so I mean if you're standing up that much compute, so if you're standing up compute for weeks at a time, you want to be. I mean, that's a better fit for infrastructure as a service workloads anyway. I mean, to be honest with you, if that were your problem, we would. Well, a couple of things. One, we would talk about. Is your data in the cloud today, or is it?
Yeah, it's in on S3.
all it's S3. Yeah, so I mean, if you wanted to do that on joint, like don't let pricing get in your way. We would figure out a way to give you, if you wanted to have like a little asterisk call on there, which is, I mean, if you're going to be running that much compute for that long a period of time. But I mean, it's EC2 pricing, right? That pricing is EC2 pricing. It's 14 cents an hour. 14 cents an hour is for, I mean, that.
It runs for 3 years.
Well, no, but that I mean, it doesn't compare to reserved instance prices, but that is basically EC2 pricing. I compete against EC2. You have to trust me on the EC2 price sheet, and so I mean that, and it's we can argue about how expensive or cheap that is, but that is it's the going rate for compute, but we charge you on kind of second granularity. So we should. I mean, if like I said, don't get hung up on that though. If you want to give us a lot of data and a lot of compute, let's figure out how to do it. Because that's what the system is designed to do and is doing right now. So I mean, there are lots of folks that are actually using this for lots of data. Are there? Okay, I'm happy to accommodate ASCII questions. God knows I've asked plenty in my own life. So, so I mean, just in terms of wrapping up, wherever my slide went off to, I think it's very unhelpfully. No, where did it? Well. All right, forget it. Google Manta, there it is. Well, you can Google Manta, and that's probably the best way to do it. But lots more information, and I would say that if you've got particular domains you're interested in, like scientific computing, we should go into more detail there, and I'll point to some stuff that we've done there specifically for that. But this is what we're doing now, effectively, is going around the different domains. The one that's a really natural fit, first kind of natural fit, is log processing for sure. If you've got log processing, this is that's what this was made to do. It does it very, very well. But we've got folks doing video analytics on it. We've got folks doing. I mean, it's not a day passes where we don't see some strange job light up Manta. You're like, wow, what the hell is that? And where somebody's thing has come up with some creative thing to go do. Fortunately, that creativity can't really extend to Bitcoin mining because Bitcoin mining is actually not profitable on this, thank God. But lots and lots and lots of applications. This, I think, one of the exciting things with this from our perspective is that Manta is one of those technologies that appeals to the creativity of its users. And so people have been and will continue to surprise us with what they're doing with this because it is a general purpose compute platform. And you can do anything you can do with general purpose compute, you can do on Manta. So, yes, questions?
Do I understand correctly that you usually always do everything in jobs, like remote jobs? Like everything you type on your own console, you basically start with an amplified or in something?
Yeah.
And then anything from that point on goes into the different nodes?
That's right. So in the example that we ran over here, where we launched a job, we'll go back over here. So what this is doing is that mfind is just creating that list of objects, and then it's piping that through locally to mjob create. Now, if that were you may say, well, wait a minute, why am I taking that list of objects, hauling it out of the cloud, and then sending the list back? So you could actually have an initial phase of this that did that mfind. So if you want to, you could have a map reduce where the first phase of that job does an mfind. And then then the whole thing would happen on the cloud. It's just a matter of, and there's as with Unix, there's a lot of kind of flexibility about how you do what, and depends on what you're trying to do. Yes?
What's your biggest issue with ZFS now, and sort of tangentially, did were you ever tempted at some to try to get into firmware?
Yeah, if I get into firmware, it's going to be with a suicide vest.
That's like your thing, though, right?
Yeah, right. Yeah, I guess jihad, maybe. The biggest issue with ZFS for us, I think that we're pushing ZFS into new dimensions. We do rollbacks all the time, because when you land in a zone, when I exit from this mlogin session, there's going to be a ZFS rollback behind me that's going to roll that zone back to what it was previously. So we're doing, so previously you do a rollback kind of like to play around, you do a rollback to kind of go restore from things. You don't really have like rollback in the data path. We do now, so we're hitting rollback hard, and that's been great. And we found and fixed a couple of issues there. But by and large, the only real way to find ZFS issues these days is to push it into some wholly new dimension like that. Take some aspect of the system that's like exists, but has not been just leaned on, and go actually lean on it. But ZFS continues to be rock solid for us. And we, fortunately, we've got the expertise to continue to go develop that. In terms of firmware, I think the firmware crisis is never going to end. I think that we're going to have. I've given up. I mean, I think that we have to deal with very unreliable hardware components. I mean, I think that the disk firmware situation actually got a little bit better. I would say that I would never buy the first rev of firmware of anything, for sure. That's, I think, what I learned there. I don't know if that's a satisfying answer or not. Yes?
I was wondering, njob can only work at one object at a time. So if I would like to have, I can't have one mblock and njob that works on two objects, or is it?
No, that's how it works. So this mjob is actually operating on all 300 of those objects.
So it's creating 300 zones.
300 zones.
Okay.
So this, sorry, I should explain this. So this map phase, this TR pipe, sort pipe unique, that is landing on 300 zones in parallel.
Okay.
Asterisk, not true big data. I know. These are just man pages. Maybe I'll create some terabyte-sized man pages just so we can. And then the reduce phase, I've got one reducer here. So this is running in one zone. It's being